In this video, we're going to go ahead and cover section 10.5, Rotation of Conics, still part of chapter 10, Topics in Analytic Geometry. FYI, this one is the examples are lengthy, so we're going to actually do one part of another and then one really quick one, and we'll probably finish the second one in class because it's kind of long, yeah? Here we go. And by the way, these are also pre-done for us to save some of that time. We have what is rotation of conics? So this is basically a process or procedure that gets rid of one of the terms, namely the xy term. And the reason we do that is because conics are not always centered at, on our xy axis. Sometimes they're kind of like slanted or diagonal looking. So like for instance, our hyperbolas, yeah, sure, the hyperbola, we had either horizontal or vertical, but often in real world situations, the hyperbola is more like slanted. So because it's slanted, we need to kind of redefine the axis to make it parallel to those axes, if that makes any sense. So we do this by rotating the axis, and we denote it as x prime and y prime. So this little like dash thing here, it means prime. It's another version of the x axis and the y axis. So here we go. Here is the process to do this, and it's kind of lengthy. Okay, make sure you get all this down. The process to rotate the axis to eliminate that term is we're going to start with the general second degree equation. So generally, you have something kind of like this, and of course b is not equal to 0, and we're going to rewrite it with primes. So you'll notice that from this one to this one is no longer there. Okay. To rotate the axis through some angle, we use the following formula. Cotangent of 2 theta, if you want to put that in parentheses, you can, it's up to you. And this is defined or it's equal to a minus c divided by b. So we take these coefficients and we plug them in, and we're going to get well, we should be able to find our angle. So whatever you get, you find where where 2 theta is equal to that, divide by 2, and that gives you the angle that we're rotating by. Okay. The new coefficients of the new equation are given by making the following substitutions. So once we have our angle, we can substitute it into these two equations, and that will give us x and y in terms of x prime and y prime. So in terms of the new axis. Okay. And final note, if this term is not eliminated when you get your equation, try again. You probably made a mistake, okay? Because it should be eliminated. So let's go ahead and do an example. We'll go through an example, I should say. This example is 2 pages long, which again is why I went ahead and just did it for us, and we're going to go through it. Okay, so let's see if we can kind of understand hopefully what's going on here. I did put up here, recall that this is our second degree equation, ax squared plus bxy plus cy squared plus dx plus ey plus f equals 0. Okay, so the example says we're going to rotate the axis to eliminate the xy term in the equation xy plus 6 is equal to 0. Then we're going to write the equation standard form and sketch its graph. Okay, so for this one, you will notice that we have a very simple graph, xy plus 6. Oh, excuse me. And if you remember our rules from before, basically this will be a hyperbola. Okay, um, so let's see. We have the following. We're going to start by finding the angle, and I just kind of put the steps here. We're going to find theta to see what angle we're rotating this axis by. So according to what I have here, and again, let me try to get that whole thing on there. A is the first term. We don't have an x squared term, so a is 0. B is this term right here. We do have the xy term. Not sure why it keeps doing that. We do have the xy term, so that's just a 1, so b equals 1. Then c is the cy squared, which again we do not have, so that's just equal to 0. So we're going to plug those numbers into the formula, which is, again, this is our formula right here. Cotangent of 2 theta is equal to a minus c over b. We plug everything in and we get 0. Okay, so how do we work that out again? So again, I kind of broke this part down for us just because it's been a while. What we do is we take cotangent of 2 theta, so this part is equal to 0, which means that cotangent, if you remember, is x divided by y. So where is on my unit circle, and you can do that real quickly if you want. On my unit circle, where is x divided by y going to be equal to 0? Well, remember we have 1, 0 here, we have 0, 1 here, negative 1, 0, and then we have 0, negative 1. So we're dividing x by y. So cotangent is x over y. And you don't have to write this down if you don't want to, but just to kind of, heads up there. So it looks like none of that is going to work out for us too well. Well, actually, no, I'm sorry. Yeah, we have it right here, because if we take 0 divided by 1, we get 0. So it actually happens at pi halves. So that's why you have this angle, in this case 2 theta, is equal to pi halves. But of course, we don't want 2 theta, we want theta. So we divide this by 2 to get rid of the 2. And I did not put that here because I kind of want to show it. You divide this by 2, so you have to divide this side by 2 also. Think of it like 1 over 2. So that gives us that theta is pi over 4. Okay, so this is the angle that the axis is going to rotate. In other words, these axes, yeah, plural, are going to rotate 45 degrees. So they're probably going to be something like this, okay? But anyway, let's move on. So once we find the angle, we have to find the equation in terms of x prime, y prime. So what we do is we use these formulas, okay? And we just plug everything in. And I'm going to focus on the x part because on the y, I kind of forgot about it. And I'm like, oh, yeah. So it's kind of squished here. But basically, all I did is I took that pi over 4 and I plugged it into theta. So there's theta, there's pi over 4, pi over 4. You work it out. We know that cosine of pi over 4 is square root of 2 over 2. Same with the sine, so square root of 2 over 2. And for this, I'm actually going to rewrite this. Usually, this is how we used to do it. But because we're trying to go to standard form of the equation, you don't want to have any extra numbers on the top. So we're going to use this form where the radical stays on the bottom. So x prime over square root of 2, y prime over square root of 2. And if we combine this, we get this equation right here. So this is the goal for this part, okay? We do the same thing with y, and it's, again, I'm so sorry, it's all squished here. But it's the same thing. You plug in pi over 4, we get basically the same thing, except instead of a minus, this one has a plus. So kind of the same deal. That one has a minus, that has a plus. Okay. Now what do we need those for? Well, the third step for this is to plug those values into our original equation. So the original equation is xy plus 6 equals 0. That's from the way beginning. And what I'm going to do is I'm going to plug this part into x. So there's x is all right here. So this part is x times the y into the y. So times y and then just plus 6. So that's what I did here. I'm plugging in what it's equal to into its corresponding spot. Okay, and then we just multiply this out. You will notice that for the top part, we're multiplying the top times the top. So you actually have a difference of squares here. You have x prime minus y prime times x prime plus y prime. If you would like, you can also FOIL this, and you will find that you still get the same answer that I have right here, okay, namely a difference of squares. So this times this is that when I multiply the inside and the outside, they end up coming out to 0. So we end up with just this y prime times y prime, which is negative y prime squared because of that minus. And of course, the bottom is a little bit easier. Square root of 2 times square root of 2 is just 2. Bring down the 6 equal to 0. Okay, so at this point, we're almost done. Now we just need to rewrite this in standard form. So I move the 6 over, okay? So subtract 6 from both sides. If you want, I can do that right here. And we're left with this, and it's still not quite in standard form because standard form has a 1 over here. So you'll see here for the fourth part, I want to rewrite this in standard form. So how do I do that? Well, I divide everything by negative 6. So negative 6, negative 6. Now we have the 1, and then 2 times negative 6 is negative 12. Okay, so we are a little over halfway done with this one problem. And here is example 1 continued. Okay, so let's cover that so we're not overwhelmed. I went ahead and separated it now. So I did x prime square over negative 12. Y prime square over negative 12 is equal to 1. And this looks weird because you don't want to have negatives on the bottom because something's going to change there. So from here to here, what I did is I went ahead and simplified this. Negative divided by negative is a positive, which means my y should probably be first because this one's going to stay negative. So Here we rearranged it so that we have it in the format that we want, where you have something squared minus the other one squared. And this is the format of a hyperbola. Okay, so that's why I went ahead and rewrote it that way. And then from there, we can see that a squared is 12, b squared is also 12. If you wanted to get a, it would be the square root of 12, same with b. Okay, so I went ahead and just kind of rewrote all this stuff here. This part right here is, well, let's cover that. Oh, let's do this. That's fine. So this part right here is just the same thing, but with a square root in case you want to see it like, something squared. These two are the same though, because if you kind of get rid of these here, you end up with a 12. You'll also notice that the y is first, so that means that this is going to be a vertical hyperbola in terms of what we're used to, okay? From here, you can see that the center in terms of x and y prime, okay, is 0, 0, and then I should probably put that. This is x prime, y prime, because that's what I have here, okay? And the vertices, since it's vertical, are going to be 0, comma square root of 12, 0, comma negative square root of 12. So remember that the vertices we get from the a value, and in this case, our a value is square root of 12, okay? So here's kind of a real quick, just super quick version of what this might look like in the xy plane for prime, okay? And of course, this is actually going to be tilted. You're going to see at the end, but I just want to show you real quick. So my center, 0, 0. My vertex is a spaces away. So this right here is a spaces away. This is a spaces away. And again, a is just square root of 12. Okay, so that's why I have these 2 points here. We're not done because we still have to sketch it in like, what it might actually look like. So in the normal axis, which is our xy, to find the corresponding vertices, so to find these, because it's kind of hard to visualize exactly where it's going to land slanted, we have to use the xy equations we found earlier. So that is step number 5, to find our corresponding x and y vertices. How do we do that? Well, we take our point, so 0 square root of 12 is one of the vertex points, and we're going to convert it to xy. So we're going to plug it back into this one that I found earlier. So x prime is 0, so 0. Y prime is square root of 12 minus square root of 12 over square root of 12. If we simplify this, the 0 goes away. Negative divided by a positive is negative 1, since they're the same thing. So in my xy plane, we have a negative 1, okay? And then for the y value, you do the same thing, but now we're adding. So again, this is the equation for that one, which we found earlier. So we end up doing 0 plus square root of 12, and that just gives us 1. And that's where we get this point here, negative 1 comma 1. And that's one vertex point. This is one of the vertex points. I should have put that here. Okay, for our xy plane. We do the same thing with the second point. So the second point is 0, negative square root of 2 in terms of x prime, y prime. And, I'm not going to go through that. It's the same deal. We just plug everything in, and we get this point now, 1, negative 1. So this is the other vertex point, okay? So we have 2, and that means that these points are going to be exactly where these points would be in the other axis. So here is what it looks like now. So it comes all together. The last step is to sketch it. So I'm going to cover this right now because the sketch is the kind of the end point, the end goal here. Get this straight as straight as I can get it. So this right here is our xy plane, okay? And you will notice that on the xy plane, at 1, negative 1, that's where we have one of the vertex points, as we found up here. Sorry, you can't see it. Right here. So there's the first one, 1, negative 1. The other vertex point is at negative 1, 1, which is this point. Okay, so those are lined up so far, but how does that apply to the other axis that we keep talking about? Okay, so you'll notice that these vertex points are not horizontal, they're not vertical, they're actually diagonal. So what I did is I actually lined up my something here, my Naruto thing here that I use for the straight edge, and I went ahead and drew the axis through this, and then I drew my other one through this. So this axis right here, and I guess I can kind of color it, but you can see what I'm talking about. this axis right here, this is what we're talking about as far as rotating the axis, because now we have our hyperbola centered on that. This axis is going to be our x prime, y prime axis. In other words, if I were to rotate this x and this y axis, it lands here, and now my hyperbola is perfectly centered on it. Okay, and you will notice that the vertice for this one and for this one, if you use this right here, okay, it's between -1 and -2, between 1 and 2, and that point right there is actually the square root of 2's that we were, I'm sorry, square root of 12 that we found earlier. Okay, and yeah, that's kind of how this works. Interesting, right? Actually, let me think. I think I might have, the square root of 12 is about 3. Oh, you know what? Yeah, I'm a little bit off here. So this should actually be, let me see. Let's just change this to a 3, because square root of 12 is going to be a little bit over 3. So we'll say this is like 2, and this right here is 1. Yeah, there we go. That looks a little bit better. There we go. So ignore those. But yeah, so anyway, nothing too picky about that. But my point is that you do have to, these should line up, and this is what I mean by the rotation. It's not an easy concept to grasp. So again, if you have questions, please let me know. We're probably going to do the parabola and the ellipse in class, because we're not going to have time to cover it in this one. But there you go. There is the process. Let's go ahead and look at the next one. I believe the next one is the one I started, and then I said we're going to finish in class, because as you can see, these do take some time to do. Okay, so for example, 2, we're actually going to rotate the axis to eliminate the xy term for a different equation, which I believe is I want to say it's an ellipse. Yes, this one's an ellipse. So there it is, and I guess I can go over just real quickly, just the beginning anyway. So in this one, we do have our A, B, and our C. This is A, this is B, this is C. Notice that B has a square root of 3 in it. So what I did here is I went ahead and plugged them into my formula, like so. And we get that, oh, this is getting very blurry. We get that A minus C is 12 minus 28 over 16 square root of 3. 12 minus 28 is just 16, so you'll notice that these are going to give me a 1. Excuse my mess here. So we end up with 1 over square root of 3. Now here, again, you have to recall that cotangent is x over y. So in other words, where is my x divided by y going to give me 1 over square root of 3? I'm not going to go too much into the unit circle part here, but it does happen at pi over 3. So when we go over this in class, I'll show this again just to kind of put forth why this is it. This is pi over 3. Okay. And of course, we do the same thing. So 2 theta is equal to that. We divide both sides by 2, which gives us pi over 6. Okay. And the step after this is where it gets a little bit, it starts to get interesting, because you would plug this into, again, to your equations, which gives us the following. We get x is equal to all of this, just plug that in, work it out, and you get this here. Same thing with the y, plug it in, work it out, and you get this here. And then you have to plug those numbers, so x and y, or I'm sorry, not numbers, those expressions into the original. So this is going to take some time. Okay, so we will continue this one at this point. This right here is our original equation up here, all this. But you'll notice that there's quite a few, foils that we're going to have to do here. So we'll go ahead and finish that in class, and also because there's definitely not enough room to do that here. So there you go. Let's go ahead and do the last part of this section here. It's called invariance under rotation. So what the heck does that mean? So an invariant under rotation is basically a I don't want to say variable, but a part of the equation that is not going to change. So it's gonna stay the same in both. So we do have some rotation invariants, and they are the following, without going into too much detail here. Basically, your f is going to stay the same. So this part right here is the same as the original. Okay. If you add your A and your C, so these two together, this plus this, you're going to get the same thing that you get adding A prime plus C prime. And finally, we have the discriminant. So the discriminant, going back to parabolas in our algebra 2 days, determined whether a parabola was um, had two solutions, one solution, or no solutions. Here, the discriminant, which can be written as in our original or the prime version, will tell us whether or not, or will tell us what type of conic this the problem is. Okay, so that's what we're going to use that for. And I do have a very quick example down here. Let's go ahead and look at this part first, though. So if you plug in your values into this to the discriminant, if it's negative, it's an ellipse or a circle. If it's equal to 0, it's a parabola. And if it's greater than 0, so positive, it's going to be a hyperbola. So final example, and then we'll go ahead and end this video, is right here. And it's super short. It actually fits on like 2.5 lines or so. It says classify this guy. So we have 2x squared minus 3xy plus 2y squared minus 2x. We just found the a, b, and the c. So a is 2, b is -3, and c is 2. Plug them in. So we get b squared minus 4ac, -3 squared minus 4 times 2 times 2. You're just plugging in these values here. And that's going to give us 9 minus 4 times 2 times 2 is 16, which gives us -7, which is negative, right? So it's going to be an ellipse or a circle. And that's it. So if you have any questions, again, let me know. This one is kind of a weird concept. It's a little weird, yeah? So let me know in class if you have more questions. We will continue that example too, and maybe do a parabola if we have some time. I want to say Wednesday or Friday. So we'll see you guys. And if you have any questions, again, please let me know.